Welcome to a lesson with Dr. Powell. Let's take a look at a generalization of Green's theorem. So just as we can take a line integral along a curve whose boundary is a surface S, and that can be equated to actually just taking the surface integral of another vector field that's derived from the one that we're taking a line integral of, we can do a similar thing between a surface integral and a volume, a triple integral here. Let's suppose that our surface is enclosed completely, just like a loop is in this curve is like a loop that's enclosed, and it's the boundary of S. So let's suppose that our surface encloses or borders the volume V. So the surface could be a box, could be a sphere, anything like that, and we have the volume inside of it. So somehow we can change our vector field that we have for our surface and change it into another one for the volume. And the idea of it is exactly analogous to what happened over here for Green's theorem. So let's suppose that we start with a surface integral. So something along the lines of dy dz, dz dx, dx dy, and then we can have our different components here for a differential two form. Perhaps we'll just label them as f, g, and h, suppose. And we would like to take this and change it to something that we can integrate over a volume. Okay, now when we take a look at this, it's the same basic idea. So imagine on one part of the surface you have a piece, and if you go directly through it, maybe in the direction of x, maybe positive x is in this direction, maybe, and then over here you have another part of the surface. So maybe a piece over here is like dy dz, and over here it's going to be like the reverse orientation of it, or negative. So, but that can be accounted for by that negative can be accounted for by switching these according to the orientation operator, the wedge. So we could do that and think about that concretely. But the nice thing about that is, without going into the details of that, is just think it's very analogous to what we were doing before. To get the new vector field, all we have to do is just change this f to a df and wedge it. Change that g to a dg and wedge it. Change that h to a dh and wedge it. And that's all we do. It's the same thing. It's kind of nice. Stoke's theorem and Green's theorem are really the same theorem, and they really function the exact same way. So, and the idea behind it, why this works, is the exact same as why it works for Green's theorem. And so taking a look at this, in fact, we could think of df as being fx dx plus fy dy plus fz dz after taking a dot product here. Notice that the dx is the only thing that'll survive the wedge. And so we end up just getting fx dx wedge dy dz. Over here, the only thing that'll survive the wedge is actually gy dy. And the only thing here that'll survive the wedge process is hz dz. And then all we have to do is just switch all this so it looks like the right order of x, y, and z. First guy is great. Second guy, let's think. Well, to make this work right, we need to we switch the dx and the dz. That's one switch. So that changes the sign. So that would be dy dx dz. But then we have another switch. There's two switches. If you switch twice, every time you switch, it's like changing your perspective or your orientation of the little of the volume or whatever we're looking at. And so actually this ends up being a positive volume here, dx, dy, dz. So we just leave it alone. It's just plus gy. All right. Now, what about this next guy over here? Same thing with switching things around. In fact, we switch the dz to in between, and then over there, that's also two switches again. So we just have plus hz. And all this is just with a dx, dy, dz, kind of nice. In fact, oftentimes in textbooks, that's all they give you. They just say, hey, look, this is the formula for Stoke's theorem, or for how you move from here to here, you just do this. And they don't kind of give you the details of what's happening with this. However, this is a lot more generalized, and it can be used in many different contexts and in many different dimensions even. Stoke's theorem is generalized to even like, thinking of things in terms of 4, 5, 6, 7, 8 dimensions. It's the same idea that holds. It's kind of nice to fit everything into one umbrella. However, this is kind of the idea here. You just be taking the triple integral of this guy in order to compute the surface integral of this guy. So this is a differential 2 form. This right here, you could think of it as a differential 3 form. Differential 3 forms when we're just done with x, y, and z are not very fascinating or interesting. However, if we bumped up a dimension, maybe perhaps with another variable, then that becomes a little bit more interesting. But for us, you could call this a differential 3 form if you wanted to. But that's kind of the basic schematic. We'll look at some examples of this. Thanks for watching.